Okay, let's get started. So we are going to talk about Ising model, and specifically we are going to talk about theory in physics, which is known as mean field theory. So the first thing I'm going to tell you, so last time we looked at Ising model from an intuitive perspective. We looked at the droplet argument. And the idea in the droplet argument was that if you create a surface in 1D, the size of the surface is kind of limited, right? In 1D, how much surface area can you have? It's limited, right? It's just the edge. That's not going to change if your domain is bigger. But in 2D, so think about it. In 1D, what is a circle? It is just like two edges, right? In 2D, a circle is a circle. And if you have a higher radius, the perimeter of the circumference of the circle becomes higher and higher. In 3D, it becomes even higher, right? That's the intuitive idea. So the energy cost scales with the surface, which is limited in 1D. And in 2D, the energy cost grows with the length, with the radius, right? That's the basic intuitive idea. But now let's try to look at it more mathematically and see why it is so hard. Why is it that still there have been Nobel Prizes, or there might be more for this problem? So again, let me remind you the Hamiltonian, or the energy of a microstate. That's E nu is equal to minus mu, some external field H. And this couples with every spin. And then I have some exchange term, which is Jij Si Sj. And we are going to look at the case where Jij is equal to 1 if you can pick up your thing. Maybe that one. So if Aidan's answer got stapled with someone else, please look at the back of your answer sheet. Maybe you find Aidan's. So this is the energy of a microstate, right? And what are we trying to do? The main problem we are trying to do is to calculate the average value of the spin versus temperature, right? This is what we are trying to show. This is the whole thing about phase transitions, right? Is this thing non-zero? Is this thing zero? And I showed you through the Pearl's droplet argument that for 1D, it looks like this, 1D, it stays zero.
What is delta?
Huh? Where is delta?
Summation of delta.
S. So, and in 2D, it goes something like this. In 3D, it goes something like this, right? So this is the T critical for 2D, and this is some T critical for 3D, and T critical for 1D is 0, right? This is, we saw it intuitively. Now let's try to do it mathematically. In order to mathematically do it, I need to calculate average of S. Now you are all StatMech gurus at this point. You know how to calculate average of S, right? How would you do average of S? In order to calculate average of S over all spins. Yeah, go ahead.
So does the slope of the curve decrease?
No claims about that. No claims about that. I don't know. Right now, the droplet argument has only shown us that it goes to 0, right? We don't know about the slope or the curvature. Those are very hard questions. So let's see. And I don't think I can answer that in this course, because now you will see why it's so hard. And mean field theory will give you a sense of that. In higher dimension, mean field theory can get everything exactly as the dimension goes to infinity. But in 1D, it's actually really, really hard. Those of you who are interested can look at the exact solution, which is Chandler's chapter on this problem. The first problem in the chapter and exercises kind of walks through on Sagar's proof. So if you really like it, work through that, see for yourself, and you will get a result. But otherwise, I think this slope is correct, but I won't make any claim. So in order to do average S, since in this Hamiltonian arca, there is nothing special about any spin, right? If Jij dependent on which I and J you were, then the spins would be different, right? But Jij does not. Jij just depends on the distance between spins, right? So we can say that this is going to be the average value of any spin can be simply calculated by looking at the average of the first spin, right? Even though things are interacting with each other, This is because if you look at this energy Hamiltonian that I wrote over here, every spin talks to the same edge, right? Every spin talks to every other spin. It's the distance between the spins that matter, right? So we have to calculate the average value of one spin. How do I calculate the average value of one spin given this definition of the energy in a microstate? Any ideas? How do I calculate the average of anything in StatMech? Sum over microstates, right? You look at the value of S1 in a particular microstate, you multiply with the probability of that microstate, right? And then you have to do all of it. Now that's going to be a terrible, terrible problem, right? Why? Because what does summing over microstate mean here? Even though you're talking about one spin, when you're talking about microstate, you have to look at the configuration of every other spin in the system, right? So we are saying that on an average, Vedant behaves the same as Nick, the same as Arka. But anytime Vedant's behavior is a function of everything else that's going on in the classroom, right? So we have to average over everything else. So this microstate means that S1, S2, Sn is equal to plus minus 1. You have to sum all of them. In each of them, you have to look at whatever value S1 takes. So if it was just S1 in the summation, then the sum won't matter, right? Because it's just S1. But the problem comes from e to the power E nu, e to the power minus beta E nu. So, right, what is P nu? P nu is e to the power minus beta E nu divided by the partition function. Here, you can take your thing. So let me write this down on the next page. So we have average value of S1 is equal to summing over all microstates, S1, S2, Sn is equal to plus minus 1. The value of S1 in that microstate multiplied by the probability. What is the probability? That is e to the power minus beta E nu divided by Z. 1 over Z we can bring outside the summation, right? So it stays like this. So average value of S1 is going to be summation S1, S2, Sn is equal to plus minus 1, S1 e to the power minus beta. And this is where it gets complicated. We have minus mu h s k. Let's use a dummy index inside here, k. It's the same Hamiltonian, but instead of I am using k. So k, sk. You can pick up your homework, Arman. That's the first part coupled to the external magnetic field. And then we have the second part, which is minus. Now, instead of ij, I will have kj, jkj, sk, sj. This is a terrible equation to solve, right? There is no hope for doing this. You cannot do this exactly. This is the problem, right? If we could do this exactly, we would have calculated the average value of S1 at any temperature, right? And just made a plot and see everything that goes on. But this is really hard and perhaps impossible. I will use impossible with a question mark because it might be possible if you make some assumptions to calculate in a general setup. And here I am willing to assume that mod k minus j is equal to 1. So even if I'm looking at nearest neighbors, it's still very, very hard, right? So that's why we have to make approximations.
Can you get the form of the Fader curve for the average value of S with just looking at this expression?
No.
Not the
No.
mathematical
No.
expression, but just.
No, it's really hard. It's really hard. I don't think I can. Maybe you can, but I don't think I can. I don't think. If you thought this equation, you know, so Ising model came up in 1930s, or people thought, okay, this is really powerful. This can describe everything, and it looks so simple. So people tried to do all sorts of things, you know, and which led to a lot of creative science that happened. You know, sometimes in science, it helps to not do everything in an experiment or a computer simulation right away, right? It helps to do theory first and think about what's going on. So it led to a lot of creative ideas, and there might be a way that you can get to the curve if you want. But I will show you one of the first approximations that people made, which might have existed before Ising model, but we will talk about this now, which is known as mean field theory. So mean field theory, the central idea is to focus on one spin. And since Vedant asked me the last question, we will focus on Vedant. So in Vedant's world, he matters, okay? And everyone else is a blob. You see what I mean? So Vedant is walking around, singing songs in his head. And all of you are not these little delta functions. All of you are just one averaged field. And he just does not care that you have your identities. It's Vedant and rest of the world. However, before you start hating Vedant on this, turns out that Suimin is also the same way. In her own world, she matters and everything else is a blob. Okay? This is the first assumption. Second assumption, Vedant's blob and Suimin's blob are the same blob. That's kind of profound. Okay? These two assumptions, let's write it down mathematically and see what we mean. So central idea is to focus on any one spin. Why can we focus on any one spin? Because if you look at this complicated energy microstate, it does not depend. It treats this definition itself treats every spin the same way, right? There is no, if Jij was position dependent, then that would go away. But this definition itself, one moment, we will solve your problem. This itself treats every spin the same way. So we can focus on any one spin. Go ahead.
Would you be able to make the second assumption if it wasn't for the equal a priori probability hypothesis?
Oh, the second assumption is terrible.
Or is it independent of?
It's independent. Nothing, you can do nothing if equally a priori did not hold true. We could not talk about canonical ensemble. So that's always needed. But the second assumption is even weaker. You will see why. So the first idea, there are two central ideas. So one is to focus on any one spin and treat the role of all other spins as an averaged field. So that's the first assumption. And the second assumption, I'm thinking if I can really write it down right now, or will it not be clear? 1 second. Actually, yeah, this is, I will not call it 1 and 2. This is the central idea, okay? To focus on any one spin and treat the role of all other spins as an averaged field, okay? So this is why you can see why it's called a mean field, right? You're looking at a mean field arising from everything else. So, and this averaged field, which is same for Margot, your homework. All spins. And everyone, please check at the back of your homework or somewhere else if I stapled Aidan's, because he writes in like his Aidan's homework as the opposite of Kinjal's homework, and Kiet's homework, they are very brief. So this time I printed Kinjal's homework like 4 on one side, and still it was like a lot of pages. That's fine. You do you. So, but Aidan's 1 page might have stapled by somewhere. So please check for it. I have a grade, so don't worry too much. We'll see. So let's start. So how are we going to implement this idea? So let's look at equation 1, which is our E nu, and let's write it down. So E nu is minus mu h summation Si. And in the mean field theory approach, we will keep the external field, which allows us to deal with that. In the Proyles droplet argument, we had removed it. And now we are thinking about summation I not equal to j, jij, si, fj. And for now, I'm not even going to assume nearest neighbor. I can generalize it over here. So pay attention as to one next thing that I'm going to do is to write it down as summation si. And this thing is actually a double summation, right? You are summing over I, and then you are summing over j not equal to I. When you do this, the si can come out, right? It can sit outside the first summation, inner summation, correct? And this one becomes jij, fj, right? So now look at the structure of this thing. here you have, in the first summation, you have a summation SI. And in the second summation, you also have a summation SI, right? Is that in the first summation, you have nothing else. It's just a 1. In the second summation, you have some other summation inside, right? So we can write it down in an integrated manner as the follows. We can write it down as, we can write it down as minus summation I SI mu H, right? Minus I summation SI again, but this time it's not a mu H, it's another summation, which is J not equal to I, Jij, Fj, right? And now, so if you look at the structure, both of them have summation SI multiplied by something else. So, right, we can integrate it together. So when we integrate it together, so what did I have on the last page? I had E nu, I'm writing the last equation again. So I had E nu minus I SI mu H minus I SI, but now there is also a J not equal to I, Jij, Fj, right? And I can write it down in the following manner. Summation I SI mu H plus summation J not equal to I, Jij, Fj. Okay. So if E nu is equal to this, we can rewrite this E nu by saying that this is I SI multiplied by some HI, where HI is all of this inside the summation, right? We just call it HI, it's just giving it a name. So this HI here now is site dependent external field. So if you just look at the form of equation 2, and what is HI? Let me write it down as equation 3. HI is equal to mu H plus summation J not equal to I, Jij, Si. So why is equation 2 lucrative? Why does it look nice? Huh? There is no exchange term, right? But isn't there any exchange term or not? The exchange term is hidden in the site-dependent external magnetic field, right? So if HI was actually independent of I, then we would be golden, right? Then we could do this complicated equation that I wrote on last page. We could calculate it because every site is just independent. There is no interaction of anything else. The problem is that HI itself is kind of cheating. It looks like a Ising model. So equation 2 looks like Ising model with no interactions, but that's not true. So that's fake news. That's correct. Yeah, that's correct. Right? So that's not true. We have a problem. So this does not really solve our problem. So we have to make a few more assumptions to really get started with this. And by the way, I also made another mistake. This is, I want to put a mu over here. So mu HI is equal to mu H plus summation J not equal to I Fij. Okay, so we want to keep the same form. So let's look at this HI. So HI is an instantaneous site-dependent external field, which takes into account the interaction. So this is equation 3. So if you divide equation 3 by mu both sides, what do you get? You get HI is equal to H plus summation J not equal to I, Jij, Fj by mu. Okay, this is equation 4. Now we can make our second assumption. What we are going to do is to look at the mean value of HI. Right, averaging over thermal ensemble, thermal noise and everything. So mean value of HI is going to be mean value of H. What is the mean value of H? H, it's an external field, it does not depend. Plus mean value of all of this, summation. mean value of summation j not equal to I, jij, fj by mu. Does jij depend on thermal noise or anything? No, jij is independent. Does mu depend on anything? No, those things can go outside. So this becomes hi is equal to h plus jij by mu summation j not equal to I, average value of fj. Okay. This equation 5 is super important. I'm going to write it on the next page and then we'll start from there.
It should be summation jij, j not. So the jij value should be inside the summation.
Sure. Yeah, it does not depend on the averaging, but it has to be inside, you're correct, multiplied by jij. Okay. So let's write it down on the next page. So we have average value of the instantaneous field at a given site is h plus summation j not equal to I, and I can just keep the mu also inside. It doesn't matter, you know, it's a constant, multiplied by summation sj. Now, here's the subtle point. And if you are really with me, then this will be obvious. Otherwise, we'll be like, wait, what did he do? Si is not equal to fj in general, right? Because spins can take different values. But average Si is equal to average Fj in general. We have made this point a few times already in today's class, right? This is not even mean field or anything. Every spin is the same. On an average, Vedant's behavior is the same as Alex's behavior, right? On an average, even with the complicated interaction that we wrote down, right? That is due to the nature of the interaction. If you look at the Hamiltonian, there is no jij depends on the distance between I and j, right? It does not depend on what is I and what is j, right? And h term is also I independent. So this makes things quite nice because now we can say hi is equal to h plus j not equal to I, jij by mu si, and si does not depend on the summation, right? So that can be brought outside the summation. So this means average value of hi is equal to h plus average value of si summation I not equal to j, jij by mu. We will assume something now, something about the structure of jij of the interaction term. We will say that jij is equal to 1 if ij are nearest neighbors, 0 otherwise. And this framework is very general because this, so far we haven't said anything about 1D, 2D, 3D, 4D, right? This could work in any dimension. So it's really powerful. So first we assume this, and second we say number of nearest neighbors is equal to small z. Okay, so this equation number 6, with these two things can be written as average value of hi is equal to h plus average value of si. What will this summation become now? Go ahead, Sophia.
How come you can pull out the SI out of the sum?
Yeah, so that is the point. So on an, if you look, you have, for that, you have to go back for this. And that's why I keep saying it's a good question because it's a subtle one. If you look at this interaction, every I is experiencing the same magnetic field, right? Every I is interacting with its neighbors as per the same jij, right? So what matters here is the difference between I and j. The location of I does not matter. The location of j does not matter. So on an average, Si will be the same as Fj. And if that is true, there is no point in dangling this Fj inside the bracket because this is exactly average Si. And we are not summing over I, we are summing over j, right? That's this point. We're summing over j. That's why it can be brought out. But this is a point. This is a subtle point. Good. Does that help? Great. So now, given these two things that jij is equal to 1 if you are nearest neighbor, 0 otherwise, and you have Z nearest neighbors, what should be the value of this summation? Z by mu, right? So this is Z by mu, because it will be 1 Z number of times. It will be 1 by mu Z number of times, and every other time it will be 0. So it's just Z by mu. So now we are doing something. We got somewhere interesting, and we are nearly there to solve our problem. There is a bit more math that remains. And by the way, this Z will be 2 for 1D. It will be 4 for 2D square lattice. It will be 6 for 3D simple cubic, right? So we can deal with different lattices by just increasing the value of Z. So let me write down equation 7 again on the next page. So equation 7 was average value of the spin, average value of this instantaneous magnetic field is equal to H plus JZ, average value of SI by mu. So what we would really like is if magically the second term here would disappear, right? Then instantaneous value of HI would be H and everything would be great. We would have no problem. And that would happen only at very high temperature, right? So you can see at very high temperature, average value of HI will start to become H.
Where is J coming from? Should be no J.
Oh yeah, I said J is equal to 1. But well, I will solve your problem. I will say this. I will say it's not 1, it's actually J. How about that? Okay. Some value, it's just a unit. It's like when a physicist gives a talk and you ask them, what's your temperature? They go, so, oh, it's 1. What does that mean? I don't know, 1. In Leonard Jones unit or something. But yeah, so we keep that as J. The interaction is J, not 1. So now, so we can think about this instantaneous magnetic field as the, so this is the instantaneous external field as the true external field plus some fluctuation from that true external field, right? Delta H. So this is our fluctuation. So delta H is going to be JZ. That's our definition of delta H, right? JZ multiplied by average value of SI divided by mu. So this is equation 7. Let's call this one as equation 8. So with this machinery, let's go back to our E nu. What was E nu? Remember, we wrote down E nu as minus mu summation SI HI, right? This was the whole idea. This is what got us started. And this was exact. There was no approximation here, right? But this exact equation can be approximated as minus mu summation I SI average value of HI, right? This is already exact. And we calculated the average value of HI. What is the average value of HI? That is H plus delta H. That is given in equation 7. So E nu is approximately minus mu summation I SI H plus JZ average value of SI divided by mu. Okay. Any questions? Go ahead, Sumin. That's what we're going to do. Did you see my notes? Have you gotten into my iPad? Maybe Pakoda is your agent. Go ahead.
So, where did the approximation exactly come in?
Oh, because if we really wanted to look at HI, we have to look at instantaneous value of SI, right? HI has, this is a good point. So HI does not have average value of FG. Approximation came in because we declared we won't look at this one. We will instead look at average of HI.
Okay.
That's where it came in, right? Because we can't, yeah, this is a very good question. So we are not looking at HI, we are looking at average value of HI. That's the approximation, right? And it's still hard, but this opens up the problem. And yeah, so we are going to do what exactly Swimin said. We are going to calculate the average value of SI with this idea. So, okay, so Swimin is going to help us. So Swimin, you want us to calculate the average value of SI. But we know that the average value of SI is going to be the same as the average value of S1, right? And that is not approximate. This is the question Sophia also asked, right? I keep emphasizing this. Average value of SI is the same for all spins. That's not approximate, that's correct. So if it's same for all spins, let's just calculate average value of S1, right? Why discriminate? So what is going to be the average value of S1? That's going to be, go to all microstates, right? Calculate the value of S1, multiply by exp of minus beta e nu, divide by all microstates, but now only look at e to the power minus beta e nu, okay? And this is what we know is complicated because e nu itself depends on all spins, right? So now we have to use this equation number 9 and see how it might benefit us in calculating this. And you will see it does not give, so the problem in calculating the SI is you don't get a clear answer. You get what is known as a transcendental equation, where you can't do it exactly, you have to do it numerically, and that's what we are going to get. So we need basically value of E nu, right, in order to calculate this. So equation 9, what is equation 9? Equation 9 is telling us that E nu is minus mu summation I SI H plus that term. But what is that term? That is delta H, right? And it's really the average value of delta H, right? So this we are calling as delta H. Okay, so let's work with this one. I know it's a bit of algebra, but just stay with me line by line. It's not that hard. So this is a summation, right? So we can explicitly write it out. The advantage now is, since we have made this approximation that delta H, we are looking at the instantaneous value of delta H. Does it depend on the site anymore? We have averaged it out, right? That is the approximation, because in reality, this delta H was site dependent. You have to think which J are you talking about, but now we have averaged it out. So that's why I don't need to dangle a I or a J in this delta H. I don't have to do that. It is just delta H. It does not depend on site. So what does E nu become? E nu becomes minus mu. We have to do the summation for every spin, right? For S1, for S2, for S3, for S4. So for S1, how is it going to look like? It will look like S1 H plus delta H. For S2, how is it going to look like? S2 H plus delta H, right? It will just go on and on. And the mean field approximation is that this delta H is the same for every spin. We do not care. We don't have to write down delta HI, delta HJ. Then the problem won't be solvable. We couldn't do anything. Minus mu S3 H plus delta H dot, 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 right? Let's call this equation number 10. I'll pause for a moment. Actually, let's call it equation 11. And this average of spin is equation 10. So we have to put equation 11 in equation 10. And that's going to be gnarly, but it turns out to be quite simple. Why should it turn out to be simple? Go ahead, Sophia, first.
What the sums of the S1 over the exponential sum? Why, if they're over the same sum, wouldn't the exponentials at each point cancel each other out.
That's exactly what. So you answered my question. You did not ask a question. You answered my. That is why it cancels out. It just doesn't matter. You have a question?
It was the exact same.
Yeah. So I don't even have to write it fully. So you guys have become smarter. 4 years ago when I taught it, my students did not appreciate that. So I had to write down like 1 page. Good. So the point here is this energy for S1 and this energy for S2, they are additive, right? And we have dealt with additive energies. When you have additive energies, you don't need to worry about all the other spins over here, right? It's just going to cancel out, right? If in doubt, ask Sophia and Nathan. Good, thank you for saving me some time. So average value of S1, therefore, can simply be calculated by just looking at S1 because S2, S3, S4 are going to cancel out. Doing S1, e to the power minus beta, this first term over here, right? What is that going to be? That's going to be minus beta minus mu h plus delta h multiplied by S1, right? And in the denominator, it will be again S1, but you don't have this S1. It will be minus beta h plus delta h S1, okay? Can we do this summation? What are the values S1 can take? Plus minus 1. Right? So this is actually really nice. We can do this explicitly. Let's write it out. When S1 is equal to 1, what is that going to be? It's going to be 1 multiplied by e to the power beta mu h plus delta h, right? When S1 is equal to minus 1, this will become minus 1 multiplied by e to the power minus beta mu h plus delta h. What will be in the denominator? Same thing, except this one will not be a minus sign, right? Because you don't have the S1 dangling. So this will be 1 e to the power. We do not have to worry about this 1 or minus 1. So this will simply be e to the power beta mu h plus delta h plus e to the power minus beta mu h plus delta h. So and remember what was delta h? We calculated the value of average delta h, right? That was jz average si by mu, right? So average delta h was jz average si by mu, right? So what we have in this numerator over here, all of this is actually beta mu h plus jz average si. Let's give average si a name. Let's give average si the name magnetization. That's what we are interested in, right? So the left-hand side is also magnetization. That's what we're interested in calculating. So jzm by mu, right? That's the summation. That's the power we have in the exponent everywhere. Since this is repeating in all the terms, let's give it a name. Let's call it x. Okay. And what equation number did I have? I had equation number 12. So equation 12. So equation 12 can now be written as m is equal to e to the power x minus e to the power minus x by e to the power x plus e to the power minus x. Anyone knows what is the name for such a function? Huh? Hyperbolic tangent, right? This is tan h. How do you all know this? Have you seen it in any other course? Which course? Let's not talk about the times you were all babies. Okay, so m is equal to tan h of x. We are basically right there now. And now we can put back the value of x. I mean, we could have just avoided it, but that's okay. So now this gives us m is equal to tan h of beta mu h plus beta j z m. And this equation 13 is the solution, it's the mean field equation. This is the mean field solution. Why is this a solution? It doesn't look like a solution. It looks like a terrible hyperbolic tan. But in this thing, what are the things that we know? Do we know beta? We're working at some temperature. Do we know mu? Yeah, if we don't, we just set it 1, right? We don't care about it. Do we know H? We do, right? It's the external field. This H is the H external, not the HI. Again, do we know beta? We do. J, it's the coupling constant, right? Do we know Z? That is problem dependent. If it's 1D, it's 2. If it's 3D, it's 6, something like that. Do we know M? No, right? So both sides have the same. So one equation, how many unknowns? 1, right? Why 2? Come on, man.
No, just
Technically two.
it's like you're using an unknown to calculate an unknown.
That's one poetic way. Do you write poetry in your side time? It's like you go on a date, it could be a pickup line, right? I want to use my unknown to calculate my unknown. Don't try that. I think I used to try things like that, and this is why it was terrible. So we have tan H of, so furthermore, let's simplify now and let's look at H is equal to 0, okay? External field is equal to 0. The same idea will apply at non-zero external field, but let's just look at external field 0. This will become M is equal to tan H of beta J Z M, right? At H is equal to 0. So we need to solve this equation. We cannot do it analytically. We will have to do it numerically or graphically. So what does it mean? That means that we will plot on the x-axis the value of M, and you can do it through a calculator. You can basically take different values of beta JZ. What does it mean to take different values of beta JZ? What it really means is, because J is fixed, right? It's some interaction parameter, and Z is fixed by the dimensionality of your parameter, of your system, right? So taking different values of beta JZ means taking different values of the temperature, right? So you do this for different values of beta JZ, and you plot tan H of beta JZ M, right? You can do this quite easily. So the first plot I'm going to make here is just M is equal to M line, right? This is M is equal to M. That's a straight line with slope 45 degrees. And now I need to plot this hyperbolic tangent of beta JZ M. So you can go and plot it in whatever software, and you will find that if beta JZ is less than 1, right? So if beta JZ is less than 1, what does that mean? That means beta is less than 1 over JZ. And what is beta? Beta is 1 over KBT, right? 1 over KBT is less than 1 over JZ. What does that mean? That means T is more than JZ by KB, right? If temperature is more than JZ by KB, that is the same as beta JZ less than 1. If you plot your hyperbolic tan for this one, you will find it looks like this. It intersects the red line at M is equal to 0, and then it never intersects it. Okay, you can just plot it and see. It will be under the X is equal to X line, Y is equal to X line. However, if beta JZ is more than 1, which is the same as saying temperature less than JZ by KB, then this one looks like follows. There is a non-trivial solution. So what did I do here? This is for beta JZ more than 1, and this is for beta JZ less than 1. So what's it telling us? It's telling us that if your temperature is lower than JZ by KB, this transcendental equation will have a solution only when the average magnetization is 0. The system cannot sustain a phase with non-zero average magnetization, right? But if the temperature is less than JZ by KB, the average magnetization can be sustained. It does not. So what is the critical temperature as per this argument? JZ by KB, right? So therefore, TC is equal to JZ by KB. This is our mean field solution. Go ahead.
What happens to the trivial solution when t is less than jz by k? What does it mean?
There is some magnetization. I'm not calculating the value of the magnetization. This is why when you ask me that question, can you make me the plot? I was like, no.
No, I'm saying that so there are two solutions, right? When t is less than beta jz is greater than 1, there are two solutions. One
Uh-huh.
0 and the other the non-trivial solution. So what does
Yeah.
this trivial solution when it goes to 0 mean?
So then you have to think about the probability of the trivial solution, which I'm not doing over here. You will see that the non-trivial solution dominates. Yeah, it's a good point. So because I'm not saying that, yeah, it's a very good question that Kinjal asked. So I'm not saying that beta jz more than 1, you will have only the non-trivial solution. You could still have m is equal to 0, right? And so we might come to that in next class, but otherwise right now the point I'm trying to make that a non-trivial solution exists, right? Which is possible. Which of these solutions we taken, I don't know yet, right?
But thinking physically again, so if I try to calculate the average average spin should have only one value for a particular system. If I try to think physically, like I can have an ensemble of copies and just calculate the value.
Yeah, so you're seeing the problems. You're basically discovering for yourself the breakdown of the mean field theory. It is already creating a problem. It is telling you there is two average magnetizations that are possible, right? It's already misleading you. And there is an even bigger breakdown of mean field theory, I would say, that you can see right now. So let's calculate the TC for different dimensions. Okay. Let me make a bit more space here. So we have, yeah, mean field theory breaks down in different ways, in drastically different ways, but it's still quite powerful and it's often the first way to tackle a problem. So TC is equal to Jz by Kb. And let's now look at problems in different dimensions. So we are going to look at 1 dimension, 2 dimension, 3 dimension. We will calculate the Z in each of these. We will look at the mean field MFTC, and we will look at the exact critical temperature, which you don't know, but I will provide you the answer. And then we will look at the error. 1D, what is Z? Number of neighbors? 2. So what is the mean field critical temperature? 2J by Kb. What is the exact critical temperature in 1D? 0. Now, this is a question I can definitely ask you on your final exam, okay? Because this you should remember. We saw it with the pulse droplet argument that in 1D, the critical temperature is 0. So what is the error? Infinite, right? Mean field theory gives you a critical temperature in 1D, which is completely wrong. In 2D, what is Z for a simple cubic lattice? For a square lattice? 4, right? So what is mean field critical temperature? 4J by Kb. What is the exact critical temperature? 2 over log of 1 plus square root of 2. That turns out to be around 2.3 J by Kb. So what is the error? It's a bit smaller than infinite percent, right? It's around 74%. Still quite a lot. And in fact, think about it, our terrible droplet argument, which Kinjal hated less than the mean field theory argument. Would you agree with that statement? No, you hated it more than this one. Which one did you hate more?
I think I hate this one more. Of course.
You hate this one more.
Because I understood the real.
But that day you seem to be hating it more, but that's fine. So, but that argument got it closer than this much, right? It was closer than this much. It was. But when you go to 3D, the number of nearest neighbors in the simple cubic lattice is 6. This becomes 6J by Kb. Does anyone know the exact answer in 3D? If you did, you would get the Nobel Prize. No one knows the exact answer in 3D. However, numerical experiments have shown that it is quite close to 4J by Kb. Right? So what is the error now? It is around 50%. So mean field theory, you can see a trend, becomes more exact as the dimensions become higher. In infinite dimensions, mean field theory is precise. Why did mean field theory break down so gloriously in 1 dimensions? Physically, what happened?
That's nearest neighbors.
No, it's more than that. There is something fundamental that we made an error in 1D. So the reason mean field theory, the main idea behind mean field theory is to ignore the fluctuations, right? You just think about the instantaneous field as average SI. And that is a good approximation as the dimensions become higher and higher. As the dimensions become higher and higher, you can ignore fluctuations. But in 1D, we saw through the droplet argument that any slightest temperature can stabilize fluctuations, right? So this basic idea that we had that average, this instantaneous HI can be replaced with average HI becomes more accurate, more exact as the dimensions increase. In low dimensions, this is a terrible idea. In 1 dimension, this is a really, really bad idea, because as we know, the entropic cost, the entropic benefit for creating a fluctuation outweighs the energetic cost, right? Similarly, when would mean field theory, so if we want mean field theory to become exact in 1 dimensions, we want Pearl's droplet theory to break down, right? When does that break down? Remember, I made that point last time. When Z becomes larger, right? When the interactions become truly infinite range, right? Then even in 1D, sustaining fluctuations can have an energetic penalty, which is so high that entropy cannot. I'm not going to write this down because it's, yeah, just try to imbibe it. So if in the Pearl's droplet argument, we had infinitely long range interactions, then the energy penalty for creating them would start to become high, right? Entropy would not help us out with it. So mean field, so the point, the take home here is, which is something you will encounter in your research, I think, irrespective of what type of research you do, that mean field theory becomes exact in 2 limits. In 2 limits, and you could have both of them at the same time. First limit we saw as dimension tends to infinity. And what is the second limit? As interactions become infinitely long range, which is kind of counterintuitive, right? Everything is talking to everything, but then you can get away with mean field theory. Interactions become infinitely long range. So people use mean field theory in different types of problems. It's used all the time. When Alex emailed the author of this guy who became very, very happy, he told Alex to read the supplement of his paper because he gives a mean field theoretic description of the negative thermal expansion problem. So people use it all the time. It's easy to do. And the same basic picture is to introduce something that takes care of the interaction in an averaged manner, right? That is the whole idea. We had H plus Jij, and we introduced the Jij as something which is averaged out. This works all the time. So here we looked at this Ising model in the simplest formulation. Ising model people have generalized in many, many different forms. There is a spin glass model, which people started doing around 30, 40 years ago, 50 years ago. There, Jij itself comes from a probability distribution. The Jij can be, it comes from a noise. So Jij can be Gaussian. And that model has its own different properties. Mean field theory does not work there. And a lot of people, specifically Phil Anderson, who got the Nobel Prize a while ago, he has a very famous essay that you might enjoy reading. It's called More is Different. It is applicable to physics, chemistry, biology, all sorts of things. It's a wonderful essay. Phil Anderson tried to solve this problem in 75 using something known as the replica trick. I will come to you in a moment, JP. But people have still been thinking on different types of modifications of Ising models. We don't want to get into that. For a lot of time, people thought these modifications are stupid. No one cares about it. But turns out when you train neural networks, one of the best way to model the training of a neural network is to model it as a spin glass, where the interactions are random. So in order to understand why deep learning works, people are going back to spin glasses, which is crazy to me that these things are happening again. So it's really, really interesting. Go ahead, JP.
Is it that when they sample from the distribution, is it still only the nearest neighbors, or is it like?
No, it's all neighbors. You can do whatever you want. You can describe. So, you could run a research group where ChatGPT would create different types of Ising model problems for you. And every year you write one paper, on one of the problems. there is a lot of richness here, right? We allowed our spins to take only plus minus one. You can make your spins take more value than plus minus one, then it is known as a Potts model, when the spin can take values which is something like 1, 2, 3, something like that. And you can do lots and lots of things with a Ising model. So mean field theory broke down in 1D. It gets better as we go to higher dimensions. I'm going to stop here. I want to leave you with a puzzle. That puzzle we are going to answer in next class, at the beginning of the class. You can go and read Chandler. He already tries to answer it. And then that puzzle will motivate us to talk very briefly about something known as renormalization group theory, for which Ken Wilson got the Nobel Prize. And that will, it's a very nice idea, which really thinks about why Ising model has sort of a fractal-like structure. That will be the last topic we cover. I'm not going to ask you questions about renormalization group theory. So the final exam, to answer your question from earlier, will stop at what we did today, okay? There will be nothing beyond this, but please do come to next class. It will help you appreciate these things better. And Tuesday's class, we will do a recap and maybe do one more topic, advanced topic. So let me start with the puzzle that I'm going to introduce next time. So if I really want to calculate, so let me write it on the next page. So puzzle for next time. If I really want to calculate the magnetization of a system, of the Ising model, where what is magnetization? Magnetization is going to every spin from 1 is equal to n, looking at the magnetic moment there, right? And calculating the value of the spin, right? This is the magnetization. If I want to calculate the average magnetization, what is that going to be? That's going to be partition function Q, canonical partition function, every microstate nu. Then you are doing I is equal to 1 to n mu Si e to the power minus beta E nu, right? This is the average value of the magnetization. Now let's think about E nu. Now this puzzle is valid only in H is equal to 0. So we are talking about 0 external field, okay? Otherwise there is no puzzle. So in H is equal to 0, what is the value of E nu? Anyone remembers? Ij, J, which depends on Ij, Si, Sj, right? So notice the structure of this E nu. If I had a particular value of the spins, S1, S2, Sn, and if I flipped every spin and I made it a minus sign, minus S1, minus S2, minus Sn, what happens to the value of E nu? Does it change?
No.
It's an even function, right? So E nu is even function for all spins, even function when you flip everything, not just flipping one spin, right? Even function of S1, Sn. So every configuration with positive m nu is equal to mu summation Si will have same probability as configuration with negative m nu, where you have mu I minus Si, right? Because E nu is the same. What does this tell us about calculating the average m using this equation? It should be 0 at any temperature. Why do we ever get a magnetization state? This is the puzzle that we will think about next time. Okay, and you can read Chandler, he talks about this. Okay, so see you on Thursday, and please look for Aidan's homework or he's gonna cry.
Since we have
Huh?
the field sort of each individual spin being a perturbation,